Most stars do not end their lives in violent explosions. Only the most massive ones detonate in supernovae, tearing themselves apart in a final moment of cosmic fury. But the vast majority, stars like our Sun, follow a different path. Their deaths are quieter, lonelier, almost meditative. Instead of erupting, they slowly shed their outer layers into space, leaving behind the exposed core, a dense, smoldering ember known as a white dwarf. A white dwarf is not a star in the usual sense. It no longer burns nuclear fuel. It no longer shines because of fusion. Instead, it glows with the trapped heat of its former life, a fading memory of atomic fire. This glowing corpse can no longer change its fate. It will cool, dim, and crystallize over billions of years, becoming colder than any winter ever imagined. But even in death, it remains extraordinary, a sun-sized mass crushed into a sphere no larger than Earth, supported solely by the quantum pressure of degenerate electrons. One day, billions of years from now, our Sun will join this silent population. It will swell into a red giant, swallow Mercury and Venus, scorch Earth, and finally shed its outer layers into a glowing planetary nebula. At its center, the leftover white dwarf will linger, small, dazzling, and endlessly dense. A reminder of what once was. White dwarfs are the quiet bones of stars, the cosmic ashes that remain after the fire burns out. And though they seem simple, they hold some of the most profound secrets of physics, quantum mechanics, stellar evolution, and the long-term fate of matter itself. To study them is to look at the universe's graveyard, but also its future. A white dwarf is the stripped-down core of a once-living star, a remnant left after all thermonuclear reactions have ceased. What remains is a sphere composed mostly of carbon and oxygen, sometimes, in the most massive cases, oxygen, neon, and magnesium. These elements are the ashes of hydrogen and helium fusion, compressed to unimaginable densities under the weight of the collapsing star. A teaspoon of this matter would weigh tons on Earth, not because it is exotic in composition, but because its atoms are squeezed so tightly that electrons no longer behave freely. Crucially, a white dwarf no longer burns fuel. There is no fusion, no internal engine, no process replenishing its energy. Instead, its structure is supported entirely by electron degeneracy pressure, a purely quantum mechanical effect. According to the Pauli exclusion principle, electrons cannot occupy the same quantum state. When gravity tries to crush the stellar core beyond a certain limit, electrons resist, not through heat or motion, but through the fundamental rules of quantum physics. This invisible pressure halts collapse and keeps the remnant intact. And yet, despite having no internal power source, white dwarfs shine. They glow because they are born extremely hot, often exceeding 100,000 degrees. Their brilliance is simply the leftover thermal energy from the star's past life, slowly radiating away over billions of years. They are not alive as stars anymore, but not dead either. They are in a prolonged afterglow, a cosmic sunset stretched across eternity. This fading luminosity is the echo of their youth. Once, these remnants powered solar systems, forged elements in their cores, and warmed ancient worlds. Now they persist as small, brilliant cinders, glowing not from creation, but from memory. To observe a white dwarf is to witness the final physical truth of stellar evolution, the quiet, dense heart that remains when everything else has burned away. The death of a typical star unfolds not in violence, but in slow, majestic transformation. For most of its life, a star shines by fusing hydrogen into helium in its core. This balance between outward radiation and inward gravity defines its stability, keeping it round, bright, and alive. But hydrogen is finite. After billions of years, depending on the star's mass, the core exhausts its fuel. Gravity begins to win. As hydrogen runs out, the core contracts, growing hotter and denser, until it reaches the temperature required to ignite helium. The outer layers respond by expanding outward dramatically. The star swells into a red giant, its radius reaching tens or hundreds of times its former size. In this swollen state, the star breathes heavily, like a creature at the end of its strength. Layers of gas drift away, stellar winds intensify, and the outer envelope becomes unstable. Eventually the star can no longer hold on to its swollen atmosphere. It releases its outer layers into space, forming a delicate, glowing structure called a planetary nebula. Despite the name, it has nothing to do with planets. It is the star's final exhalation, a vast, colorful cloud sculpted by radiation and magnetic fields. This nebula will shine for only a short cosmic moment, perhaps 10 or 20,000 years, before dissolving into the interstellar medium. From far away, a planetary nebula looks like a cosmic eye, a burning flower, a symmetrical shell of light drifting in darkness. At the center of this nebula remains the star's bare core, an object roughly the size of Earth but containing a mass comparable to that of the entire Sun. This is the newly formed white dwarf. Its density is unimaginable, atoms crushed so tightly that electrons themselves provide the pressure supporting the remnant from collapse. Without nuclear reactions, the star no longer burns. It simply cools, slowly, steadily, for billions of years. This final state is not one the star chooses but one dictated by the laws of quantum mechanics. Gravity tries to collapse the core further, but electron degeneracy pressure sets an impenetrable limit. The core cannot shrink, cannot ignite new elements, cannot evolve into anything else. It is an endpoint with no escape, the quantum boundary between something and nothing. And so the star becomes a white dwarf, a quiet, glowing monument to everything it once was. One of the most astonishing discoveries in modern astrophysics is that white dwarfs do not simply cool, they solidify. As the remnant star radiates away its stored heat over billions of years, its dense core undergoes a profound transformation. At the heart of a white dwarf, temperatures eventually fall low enough for atomic nuclei, mostly carbon and oxygen, to lock into an ordered lattice. The star begins to crystallize, not from the surface inward, but from the center outward, just as water in a lake freezes from its coldest depths. This crystallization process is governed by quantum mechanics and the extreme densities inside the star. Carbon and oxygen atoms are packed so tightly that, as they lose thermal energy, they no longer behave like a hot fluid. Instead, they arrange themselves into a rigid, geometric structure, a cosmic crystal. In essence, the dead star becomes a colossal diamond-like object suspended in space, its crystalline interior stretching thousands of kilometers across. It is not diamond in the commercial sense, but the internal structure is strikingly similar, a solid lattice of carbon under unimaginable pressure. Astronomers now believe that most white dwarfs in our galaxy are crystallized to some extent, and that this process has already begun in many nearby remnants. Even more remarkable is the realization that our own sun will eventually become one of these cosmic gems. After it sheds its outer layers and cools for several billion years, its core will crystallize into a massive, slowly cooling sphere of solid carbon and oxygen, a literal stellar diamond, shining faintly in the dark. Crystallization also changes the cooling behavior of the star. As the white dwarf transitions from liquid-like plasma to solid crystal, it releases latent heat, much like water releasing energy when it freezes. This slows the cooling process dramatically. As a result, some white dwarfs appear younger than they actually are because their temperature drops more slowly during this transition. The discovery of this cooling delay forced astronomers to revise age estimates of ancient stellar populations. To look at a crystallizing white dwarf is to witness the quiet alchemy of the universe. A star that once blazed with nuclear fire now freezes into a jewel, storing within its core the memory of everything it once illuminated. The final chapter in the life of a white dwarf unfolds on timescales so immense that they dwarf everything we understand about cosmic history. After a white dwarf has spent billions of years slowly cooling, first glowing white, then yellow, then a faint deep red, it eventually reaches a point where its remaining heat is exhausted. With no nuclear reactions to replenish its energy and no significant sources of external heating, the remnant continues its long descent toward absolute darkness. This is the theoretical birth of a black dwarf. A black dwarf is what remains when a white dwarf cools so thoroughly that it no longer emits visible light or significant infrared radiation. Its crystalline interior, once glowing with stored thermal energy, falls to temperatures mere fractions above absolute zero. The object becomes a cold, inert, pitch-black sphere about the size of Earth but with a mass comparable to that of the Sun. It is, in every meaningful sense, a stellar corpse, a remnant that no longer interacts with its surroundings except through gravity. But despite being predicted by physics, no black dwarf exists today. The universe is only 13.8 billion years old, far too young for even the oldest white dwarfs to cool completely. Calculations show that transforming a white dwarf into a true black dwarf would require at least 10 to the power of 15 years, and possibly far more. That is a million billion years, orders of magnitude longer than the current lifetime of the cosmos. To witness the formation of the first black dwarf, the universe must survive through epochs in which galaxies evaporate, stars stop forming, and even proton decay might occur. If black dwarfs ever form, they will be among the loneliest objects in the universe. They emit no light, produce no heat, and cannot be detected with current or foreseeable technologies. They would drift through space like invisible gravestones marking the locations where stars once lived. The physics governing their final evolution, whether they remain stable forever or eventually collapse through exotic quantum processes, is still uncertain. Some theories even suggest that, in unimaginable future eras, black dwarfs might be the last objects to undergo supernova-like explosions triggered by quantum tunneling. What we call a black dwarf is not simply a cold star. It is the quiet end of stellar evolution, the universe's final whisper after the lights have gone out. Although white dwarfs are often described as dead stars, their story is far from over, especially when they exist in binary systems. In these stellar partnerships, the white dwarf can exert a quiet but relentless gravitational pull on its companion, siphoning gas from its outer layers. This process, known as accretion, can transform a dormant stellar corpse into an engine of explosive activity. As hydrogen or helium-rich material spirals toward the white dwarf, it forms an accretion disk, a thin, luminous structure heated by friction and gravitational compression. Bit by bit, this captured gas settles onto the dwarf's surface. But because the white dwarf is incredibly dense, with surface gravity hundreds of thousands of times stronger than Earth's, the accumulated layer is compressed and heated to extreme temperatures. Eventually, the conditions become identical to those inside a young star. Thermonuclear fusion is sparked, but only in the thin layer of accumulated matter. This sudden ignition produces a nova, a thermonuclear surface explosion that causes the star to brighten by thousands or even millions of times. The eruption expels the outer layer of accumulated gas into space but leaves the white dwarf itself intact. In fact, this cycle can repeat: accretion, build-up, ignition, explosion. Some white dwarfs experience novae every few decades, others every few centuries. They are not destroyed, they simply flare up and return to silence. But there is a more dramatic and catastrophic outcome. If the white dwarf continues to steal gas over long periods, its mass can creep closer to a fundamental limit known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. This is the maximum mass that electron degeneracy pressure can support. Beyond this threshold, the quantum mechanical scaffolding that holds the star up collapses. The moment it exceeds this limit, whether by slow accretion or the merger of two white dwarfs, the star undergoes a runaway thermonuclear explosion. This event is a Type Ia supernova, one of the most powerful and consistent explosions in the universe. In a fraction of a second, carbon and oxygen in the core ignite uncontrollably, detonating the entire star. Unlike typical supernovae, which may leave behind neutron stars or black holes, a Type Ia supernova leaves nothing: no remnant, no core, no trace of the white dwarf that once existed. The star is completely unbound, atomized, scattered into interstellar space. These explosions are so uniform in brightness that cosmologists use them as standard candles to measure the expansion of the universe. Thus, a white dwarf can live two very different posthumous lives: the gentle temperamental flare of a nova, or the catastrophic annihilation of a Type Ia supernova. Even in their death, white dwarfs shape galaxies, seed the cosmos with heavier elements, and illuminate the deepest structure of the universe. Among the most important numbers in astrophysics is a quiet, unassuming constant: the Chandrasekhar limit, roughly 1.4 times the mass of the Sun. It represents the maximum mass that a white dwarf can possess while remaining stable. The limit is not just a boundary, it is a razor edge between existence and annihilation, a place where quantum mechanics and gravity collide head-on. Inside every white dwarf, gravity tries to crush the star into a smaller and smaller sphere. What prevents this collapse is electron degeneracy pressure, a purely quantum mechanical force that arises because electrons cannot occupy the same state. This pressure is extraordinary, strong enough to hold up a sun's worth of mass inside a body the size of Earth. But it is not infinite. As the dwarf's mass increases, gravity grows stronger, and the electrons become increasingly squeezed. At exactly 1.4 solar masses, the electrons can no longer provide enough support. The physics that sustains the white dwarf simply breaks. If a white dwarf in a binary system continues to accrete gas, or if two white dwarfs merge, and the total mass crosses this threshold, collapse becomes unavoidable. But it does not collapse quietly. Instead, the sudden compression raises the internal temperature to the point where carbon and oxygen ignite explosively. This ignition is uncontrollable, consuming the star's interior in milliseconds. The result is a Type Ia supernova, a thermonuclear detonation so powerful that it can outshine an entire galaxy. This event destroys the white dwarf completely. Nothing remains, no core, no neutron star, no black hole. The star is turned into expanding dust and heavy elements. The explosion is not only catastrophic but also extraordinarily uniform. Type Ia supernovae release nearly identical amounts of energy every time because they all occur at the same physical threshold, the Chandrasekhar limit. This consistency allows astronomers to use them as standard candles, measuring their brightness to calculate distances across the cosmos. In the late 1990s, observations of these supernovae revealed that distant explosions appeared dimmer than expected. The only explanation: the universe is expanding faster than before. This was the discovery of dark energy, one of the greatest breakthroughs in modern cosmology. It happened because white dwarfs, quietly balanced on the Chandrasekhar limit, occasionally tip into catastrophe. The Chandrasekhar limit is not just a number. It is a cosmic warning line that determines the fate of stars, shapes galaxies, and helps us measure the very expansion of space-time itself. For decades, astronomers believed that the atmospheres of white dwarfs were simple and unchanging. Their immense gravity should pull all heavy elements downward in a matter of days, leaving only hydrogen or helium floating at the top. A white dwarf surface, in theory, ought to be chemically pure. Yet modern observations with space telescopes have overturned this assumption completely. Many white dwarfs show clear traces of exotic atmospheric contamination, signatures of heavy elements such as magnesium, silicon, iron, and even rare metals that should have sunk out of sight long ago. This pollution is not random. Heavy elements cannot rise from within the star. They must fall from outside. The only plausible source is the debris of destroyed planets, moons, and asteroids. When a white dwarf forms, its planetary system does not simply disappear. Orbits become unstable, gravitational resonances shift, and surviving rocky bodies are perturbed inward. As they drift too close to the compact star, they are torn apart by tidal forces, shredded into streams of dust and gas. This material forms a disk around the white dwarf, and over time, it spirals inward, raining down onto the surface. The atmosphere of a white dwarf therefore becomes a forensic archive. Each detected element is a clue, evidence of a world that once existed. Magnesium and silicon hint at rocky crusts. Iron suggests metallic cores. Carbon-rich debris may reveal comets or icy bodies. In the most dramatic cases, astronomers can reconstruct entire planetary compositions, discovering remnants of Earth-like worlds or planets unlike anything in our solar system. Some white dwarfs host glowing disks of pulverized rock. Others show infrared excesses where warm dust continues to orbit them. A few even contain vaporized remnants of planetary cores, indicating that they consumed the last solid heart of a destroyed world. In this sense, white dwarfs provide a unique window into the fate of planetary systems. They allow us to witness the archaeology of solar systems long after their suns have died. These atmospheric mixes are not contamination, they are cosmic autopsies, revealing that the worlds around many stars do not survive their parents' death. A white dwarf, once the quiet corpse of a star, becomes the storyteller of worlds that were broken, scattered, and absorbed in the final gravitational choreography of stellar evolution. Around many white dwarfs, astronomers have discovered structures so faint and fragile that they resemble the ghosts of planetary systems. When a star collapses into a white dwarf, the gravitational balance of its system is violently disrupted. Orbits stretch, tilt, or destabilize entirely. Asteroids, moons, and even planets that once moved in stable paths can be nudged inward toward the dead star. But instead of falling whole, they are torn apart long before they reach the surface. The result is a collection of dust clouds and debris disks, thin, faint rings composed of pulverized rock, metal fragments, and vaporized minerals. These disks are not permanent structures. They constantly shift, churn, and decay as material slowly spirals inward. In some systems, astronomers observe asymmetric arcs of dust or thin, glowing filaments, evidence of rocky bodies being shredded by tidal forces only months or years earlier. Over time, these fragments drift inward like drifting ash, vanishing as they are accreted onto the white dwarf's surface. Some of the most remarkable discoveries come from white dwarfs where large objects briefly eclipse the star, producing irregular dips in brightness. These transits are jagged and chaotic, not the clean silhouettes of intact planets. Instead, they are shadows cast by disintegrating planetary remnants, objects so fractured that their edges crumble as they orbit. These are the skeletal remains of worlds, cores stripped of their mantles, metallic fragments trailing comet-like streams of dust, or rubble piles held together only by their last traces of gravity. Astronomers sometimes call these systems planetary graveyards. They reveal the violent aftermath of stellar evolution, the phase where surviving planets are slowly dismantled by gravitational tides and reduced to their final components. Some white dwarfs even show elements that indicate the destruction of Earth-like planets, iron-rich cores, silicate crusts, and water-bearing minerals. Others contain signatures of exotic worlds unlike any in our solar system. These ghost systems remind us that planetary stability is temporary. Stars die, orbits decay, and worlds that once thrived can end as drifting dust around a stellar corpse. In the faint rings and fragmented silhouettes around white dwarfs, we witness the long shadows of planetary systems that did not survive the death of their sun. At first glance, white dwarfs appear to be the quietest objects in the universe, cold, dense, motionless cinders left behind after a star has burned through its last breath. They do not roar with fusion. They do not collapse into black holes. They do not explode unless pushed beyond their limits. And yet, in their silence, they continue to shape cosmic history long after their light has faded from human sight. A white dwarf may be a dead star, but it carries the memory of everything it once was. Its mass, density, temperature, and atmosphere preserve the record of a long stellar lifetime. The nuclear reactions it endured, the elements it forged, the final collapse that stripped away its outer body. Even more haunting is the story written around it: rings of dust, arcs of shattered rock, the chemical fingerprints of planets that died in its gravitational grip. A white dwarf becomes an archivist, a cosmic historian preserving the ruins of its own solar system. These stellar remnants also continue to influence the universe in subtle but profound ways. Their slow cooling helps astronomers measure the ages of ancient star clusters. Their occasional outbursts, novae and Type Ia supernovae, seed galaxies with heavy elements and help map the expansion of the cosmos. Their atmospheres reveal what worlds once circled them, what minerals those planets contained, and whether water or metal or carbon shaped their ancient landscapes. In this quiet end state, a white dwarf becomes more than a relic. It becomes a lens through which we glimpse the distant past, a final ember of a star that once illuminated entire systems. It is not alive, but it still speaks. It does not shine with the fire of youth, yet it glows with the faint memory of a star's entire existence. Poetic closing thought. In the silence of white dwarfs there is no life, but there is history, old as the universe itself. They are the final light of ancient suns, carrying the stories of worlds that lived and died beneath their warmth.